So, what is game theory? No, I'm not talking about the hidden plot of a mysterious video game, the philosophy of games, or even just random facts about games. No, this is about a weird branch of mathematics I'm very fond of. Hi, my name is Mark Vicuna, one of the main developers for the new suite of game theory functions coming out with Wolfram's upcoming 14.2 release. This talk will cover two large categories of games, matrix games and tree games, covering basic functionality such as generation, visualization, and solving games. So, what is game theory exactly? I like to think of game theory as the mathematics of decision making. For example, I could make this talk 15 minutes long or 30 minutes long. On the other hand, you may decide to come to my talk or go to another talk that might be more interesting. This is a matrix game or simultaneous game. In this type of game, I need to choose without knowing your decision, whether you'll come or you'll go elsewhere. And you need to make a choice without knowing if I'll make a talk of 15 minutes or 30 minutes. Each combination of our decisions leads to a set of payoffs, where a payoff is basically expressing how happy each player is for a given outcome. If I have a 15-minute talk and you come to my talk, we're both pretty happy that the talk was useful and not too boring. If I have a 15-minute talk and you go elsewhere, I'll be sad my talk won't be listened to, but not too sad as I didn't put that much work into it. If I make a 30-minute talk and you come, I'll be super happy. People are so interested in game theory, but you'll likely find the talk a bit long and boring. Finally, if I make a 30-minute talk and you go elsewhere, I'll be very, very disappointed my talk was pointless with all that work. But you'll benefit from probably a more interesting talk. This information can also be better visualized using a dataset or the dedicated function, the matrix game plot. Game theory usually assumes all players are rational agents. That means that players will take actions that will maximize their expected payoff. In this small game, you can see that if I make a long talk, well, you have an advantage to go elsewhere. But if you do, well, I'll want to make a short talk. And if I do, you'll want to come back and come to my talk, which brings us back. So clearly, there's no simple solution here. If a player chooses option A, the other player will give him a reason to choose option B. And if he chooses option B, well, he'll find a reason to choose A. So if we find the equilibria of the game, you'll see that the optimal strategy is a bit complicated. So this strategy is basically saying, first I should do a short talk with a half probability, and the other half to do a long talk. So basically a coin toss. On the other hand, you should come to my talk with a half probability, and the other half go to another talk. If you think about it, there's a lot of games where that kind of strategy is necessary. For example, in a rock, paper, scissors game, if my strategy is always to play rock, you'll soon realize it's pretty easy to win by just playing paper every time. So the optimal strategy in rock, paper, scissors is also a list of probabilities. Indeed, to have the highest chance of winning, each player should randomly choose between rock, paper, and scissors. But what if you knew how long my talk was, even before choosing to come? Well, that would certainly change the situation. When decisions take place sequentially, we call these games tree games. In our example, I can decide to either make my talk 15 or 30 minutes. In each case, you'll be able to choose whether you come or you go elsewhere. This can be visualized using tree game plot, where each edge is an action, each chart is the list of payoffs for an outcome, and each round node represents a decision by a player. In this type of game, it's much easier to find the optimal strategy. We can do that from the ground up. If I have a talk of 15 minutes, you're better off coming. But if I have a talk of 30 minutes, you're better off going somewhere else. As a result, I'm better off having a talk of 15 minutes, so that at least my talk will be listened to. This solution can, of course, also be found computationally, using fine tree game strategies. So if I want my talk to be listened to as a rational agent, I should make my talk 15 minutes long. But there's so much more to explore. For example, this Dinner's Dilemma game has 6 players, and for each player, there's 3 actions. Those simple simultaneous games can get to much more complicated cases. Solving those more complicated games is definitely more computationally complex. For example, this escalation game is a tree game. The first node is a nature player, which is a probabilistic player. It chooses arbitrarily between the first and the second option, with a 0.5 probability for each. Then, player A has an information set. That means that player A will not know the difference between the choice here and the choice here, because the information for player A is the same. Same for player B. Player B cannot perceive the difference between this option and this option. In those cases, it's much more difficult to establish what is the optimal strategy. This kind of game occurs much more often in games of chance, like poker, where one player may not know what the next card is, and is not able to know what are the hands of all the other players. All these game theory features have a lot of complexity to them, and it might not be intuitive at first. That's why we have extensive documentations for all of these features. For example, the Matrix game has many different examples of games and the different options and their uses. As you can see here, we have a simple game that is a zero-sum game with 2 players, but as we progress into the documentation, it gets more and more complicated. And you'll soon be able to master all kinds of difficult games. There's also a tree game documentation, that has all these features about the different payoffs, the different probabilities, different information sets, and even combinations of those concepts. And of course, there's a lot of examples for the documentation, including also with strategies. Finally, there's also the game theory data documentation that is very extensive. In fact, all of the 49 games are explored in this documentation so that you may have a full introduction to all of these classical games. Game theory data is our function for named games. There's a total of 49 different games that you'll be able to easily study using this function. So what if you want to study the alpha roll bar game? Well, just type alpha roll bar description and you'll get a nice little description of the classical way it's usually described. There's also the alpha roll bar source that you can type to get the scientific literature concerning this game. If you're concerned about the different classes this game belongs to, you can check with classes. And as you can see, this is a matrix game. And it's also an n-player game, so we can put as many players as we want. So I'll generate a alpha roll bar game with 4 players. And there it is. There's also 2 utility functions that are worth noting. If we generate a matrix game and we find its strategy, you may verify the optimality of the strategy using verify matrix game strategy. And so that takes a game and a strategy and verify true if the strategy is indeed optimal. You can also calculate the payoffs of the strategy using the game once again and the strategy to get the payoffs. And those you'll note are expected payoffs based on the probabilities of the strategy. There's also the same equivalent for tree games. So if we generate a tree game and we get the strategy, then we can verify the optimality of the strategy with verify tree game strategy, with the game and the strategy, and calculate the payoffs of the strategy with tree game payoff, with the game and the strategy, to get the expected payoffs. Oh shoot. Well, I guess with all of that in mind, I guess it's the end of my 15-minute talk. Thank you for coming to this talk. And feel free to ask a bunch of questions. It's likely going to improve everybody's payoff. So, hi everyone. That was my talk. Now, feel free to take some time to think about it, ask your questions. I'll try to answer everything. We do have plenty of amount of time, I think. There's some questions that I've answered if they were easy to answer, but otherwise I'll just talk about them now. So I'll start with the Q&A. To what extent is game theory applied in real-world decision-making scenarios? Thank you, Matt, for that question. I would argue that game theory and game strategies are used basically all the time. It's just that people are not necessarily conscious of it. And I think in the realm of politics, in the realm of economics, people can get specialized into that kind of branch of mathematics because you get to analyze your decisions much more strongly, and you can evaluate a bit better what would be the expected payoffs and expected, well, consequences of your actions, basically. So I think definitely in those two fields and in many other fields and one more, this gets applied. I would argue that game theory is there in every decision. It's just that we don't necessarily talk about it in that way. Then for the next question, is the Lemke-Hausen algorithm now implemented? So that algorithm is based on a series of polynomial equations to solve basically matrix games. So Wolfram, we decided to name matrix games as that, but in the literature, you'll think about it as simultaneous games or normal form games. They have many different names, and we wanted to have something that is kind of intuitive to name it, so that's why we call it matrix, because that's what it is in a sense. It's the data structure behind that is just the matrix. And so going back to the question, I would say kind of what we have to solve those games is we're using those functions, I guess those polynomial equations that the Lemke-Hausen goes through, but we have several methods to go through those equations, and they don't necessarily follow that algorithm exactly. So if you, when you get the opportunity, if you can mess with the method option of that find strategy function, you'll be able to go through basically solve values and solve values, find instance, and basically all those different methods that you know from Mathematica, or from the Wolfram language, I should say. And so you'll get access to all those functions, and all of these are basically handling those polynomial equations in different ways. So I will say kind of probably if you are going through the default method, it's doing something analogous to that algorithm, but we do offer more different ways to approach that, especially for practical cases when you have like an infinite number of solutions. This may not be so practical. Then, so we use the word optimal sometimes in the documentation. We may end up removing it eventually, but optimal is a nice way, a word that people understand as like, oh, it's a good thing. But in the context of game theory, it is imprecise, I'll confess. But if you use the word equilibrium or other words, it's a bit more confusing for users sometimes. So basically, for now, we have equilibriums that we're evaluating. And so there's two types of equilibriums that we're currently looking at, which are basically just Nash equilibriums for matrix games and subgame perfect equilibriums for tree games. And those are, I guess, like the basics of game theory. Obviously, there's more equilibriums, and there's even like optimal measures, quote unquote, or metrics that we can eventually measure that do not enter into the definition of equilibrium, but could be considered optimal. So to say basically that is a loaded question, why are we using optimal? The answer is, I would say, just to make it clear that this makes sense considering rational agents. But yeah, we're focusing basically on those two basic types of equilibriums. And you can evaluate dominance. Technically, dominance just means that a option is dominating over all other options. This is not equivalent to an equilibrium. And so it is, I guess, a different assessment. So I guess hopefully that answers that question. Then, okay. So yes, so the choice of the naming find matrix game strategies or find tree game strategies. For now, we are dealing with equilibria. However, I mean, even technically, you could argue that the definition of a subgame perfect equilibria is not technically an equilibria. So we're dealing with two types of equilibria, and we're already having issues with whether we should call them equilibria or not. And the vision for that project and future updates and future small updates is that we add to those strategies based on different metrics. So we can try to find strategies that are Pareto efficient and try to find strategies that do this or that. There's different goals that agents can have in a game, and we're trying to have one function that would englobe all those different kinds of strategies. The term in the literature is a strategy. So strategy is just a sequence, a set of decisions on each action node. And so that's why we're calling them strategies and not equilibria. It's true that currently we could name them equilibria, but the vision for that function does not correspond to an equilibria because that term is too restrictive. So that's why we use the term strategies. But I understand the gripe with this. But the term strategy is used in the literature, unlike matrix games, which I think is an invention of ours. So I think strategy should be understandable. And I'm taking too much time per question. Okay. Will tooling allow variation of game parameters to observe what happens to the equilibria? Yes, I think. Ooh, I can finally use my slides. Well, not my slides, but I think I have a cool example of that somewhere. Let me try to search it up. I think that's find matrix game strategies. And that should be, I'll put that in 300%, and it's at the end. If it works, it works. If it doesn't, then you'll have wasted a bit of time with me. Players, let me full screen that. That is not in the neat examples. Okay, maybe here? Yes, that's the thing. Okay, and it's too big for the screen, but no matter, you get the idea. So this is like a fun little interactive example where you can just use manipulate and just move the literal different, like you have this game over here, and all of these are the different payoffs. You can change the payoffs as much as you want, and then depending on where you put your cursor, it can evaluate the different strategies. So obviously this is like kind of handmade, not that pretty, but you get the idea that yes, you can definitely vary the game parameters to see what it happens to the equilibria. The function is fast enough so that you can do it basically interactively. So that's a fun thing to do for sure. I think that answers. No, there's more in Q&A. Okay, hold on. Jonathan, your text suggestions, I'm not sure what you mean, like textbooks that you would want to read. I mean, we've based our, maybe I should show the fact that we have used like several textbooks in order to make that functionality, but I think more interesting is probably the fact that for all these game data games, this is probably like, if you go through like this list and try to understand these games, you're going to get a lot of information about what is possible, what is interesting in game theory. And all of those games basically have their little description that's kind of fun, and they have their source. And so obviously, I think for our users, it's going to be super interesting to just go through those articles and see where does this game come from in the scientific literature, and then this is going to get you like leveled up in terms of understanding game theory for sure. I think I finished with Q&A. I'll go to the chat. And you have my notebook. This is not in 14.1. This is in the next update. So if you have downloaded the notebook, you can try to evaluate it, but it's going to fail. But eventually it will be able to evaluate. It's just a future thing. And then, yeah, hopefully the 15-minute talk was short enough. There's obviously a lot of features here that you'll get to explore soon enough, but well, this is just an introduction. Okay, I think that's it. We have a new one in the Q&A. Oh, all right. Well, thank you for coming. It was fun. It's a fun project. I hope you have fun too. It might not be the most industry-driven tool. It's probably not going to be intended to be used by people that need very, very complex games. But in terms of the learning tool, in terms of interacting with game theory on an intuitive level, I think this is going to be a great thing to have. So hopefully you enjoy it.